Hello everyone, this is chapter 10.3 where we'll be discussing the inverse of a square matrix. So a square matrix, by the way, just means it's an n by n dimension matrix. So if we call that matrix A, then it has a multiplicative inverse, A inverse, so that's the phrasing of how you say the multiplicative inverse of a matrix A, if this holds. So multiplying A to its inverse in any order, matrix multiplication, will give us the n by n identity. And recall what that is. It's just the n by n matrix whose diagonal is 1 and all other entries are 0. And I note here that A inverse may not exist. And we'll see some cases of that actually later on. But now for this example, we want to check if B and A, these particular 2x2s, are multiplicative inverses of each other. And the way we can check that is just by multiplying them together in any order. So let's do B times A first. So notice that's first one multiplied by the second one in that specific order. And we remember how to do this. We just kind of swing one column over one at a time, multiply down, add across. So if we swing this one over, and just kind of show that a little bit. If you multiply down, add across, we get -1 plus 2, that's 1. -1 plus 1, that's 0. So far so good, it's looking like the 2x2 identity. And then swinging the next column over to 1, like that. Multiplying down, adding across gives us 0 for the first entry of that column. And then 2 minus 1 is 1 indeed. This one, and this is indeed I2. So this checks out. And it'll allow you to verify on your own that AB will also give you the same thing. But, you know, there's something I kind of want to say here. As it turns out, if multiplying one way is gives you the identity, then multiplying the other way around has to give you the identity as well. And that's kind of a well-known fact from matrix multiplication. And again, you can try this on your own, but honestly, it suffices to check one way. I know the definition here says both, but if it works one way, it has to work the other way around as well. And I can kind of show that real quick. So let's just say, for instance, we know that B times A gives us the identity. But notice if we multiply both sides by, well, I guess, let me see, how would we do this? If we multiply both sides by A and B on the left and right respectively, then we'll get this. So multiplying both sides on the right by A and on the left by, on the right by B and on the left by A. And notice here, this is just, well, that's B, so this is AB on the right. And here, really we can group this by associativity of matrix multiplication as AB times AB. So AB times AB is equal to AB. And basically what you can do is you can just multiply both sides by the inverse of AB on the right, and you'll get that AB is I, but we started with BA is I. So it's kind of technical, but it just goes to show, based on the properties of matrix multiplication, that showing one way is true, the other way is automatically true. But in practice, it's best to check both ways. So again, I'll allow you to check in this particular example that AB will also give you the 2x2 identity. Okay, so now we're going to move on to actually find out how to find the inverse given a matrix. And in particular, we'll look at 2x2s for now, and then we'll move on to higher dimensions later on in the video. All right, so as it turns out, for a 2x2 matrix, there's actually a very, very quick way of finding the multiplicative inverse. Before I show you that, though, I feel we deserve to see the kind of longer way of doing it. And in fact, kind of exploring why the longer way kind of works will show us how to find the inverse for any dimension matrix, because that shortcut for 2x2s only works for 2x2s, as it turns out. But we'll also explore that, of course, as well. So let me just say that if we want to find A inverse, such that A times A inverse is the identity, basically what we want to do is we want to multiply this to some other matrix, A inverse, that will result in the identity. And as mentioned previously, it doesn't matter which order you put them in. As long as it works one way, it must work the other way because of the multiplication properties I mentioned. So here, this is going to be our matrix A, and this is our sought after A inverse. So just to make the notation a little easier to look at, I'm going to call this ABCD. Okay? And we're going to solve for ABCD by systems of equations. If we actually multiply it out, notice what we'll get here is we'll get 1a plus 4c. So it's a plus 4c. And then I guess down here it's going to be negative a minus 3c. Over here it's going to be, so remember how that works, flipping it over, rotating the columns here over to the rows, multiplying down, adding across. We get b plus 4a. I'm sorry, b plus 4d, there we go, good. And then here negative b minus 3d. And this is equal to this identity matrix here, 1, 0, 0, 1. So what we actually get is a system of equations. We have one for a and c and one for b and d. So we actually have two systems of equations here. One system is a plus 4c and negative a minus 3c. And these must be equal to the entries that they correspond to in order for these matrices to be the same. In other words, the top entry here must be 1, the lower entry here must be 0, and we have this other system of equations, b plus 4d equals 0, and negative b minus 3d is equal to 1. Now, in this particular instance, these systems are actually very easy to solve for. So notice adding straight down, you just get right away, you get c is equal to 1. And here, adding straight down, we get d is equal to 1. Okay, plugging back in to find a, let's plug it into the top one. We get a plus 4 is equal to 1, so that means a must be negative 3. So it almost solves itself right away. This one is a really nice example. Here, if we plug this into the top one, we end up getting b is equal to, let's see, b plus 4 is equal to 0, so b must be negative 4. Perfect. So that actually tells us what the inverse is. Remember, this was our inverse. So over here, our answer will be A inverse is just the matrix whose entries are A, B, C, D. We found A, B, C, D. It's negative 3, negative 4. And C, D would be 1, 1. Perfect. Now, the really awesome thing about doing it this way is it kind of unveils basically a method to find the inverse of any matrix. Whether it's a 2 by 2 or 3 by 3, of course it has to be square though. And what you do essentially is you solve two systems at the same time. And I'm going to erase this and write something a little different. It's going to be the same thing, but the process will seem a little different. And after describing that process, we can see how this can carry over for 3 by 3s. All right, so recall we ended up with these two systems of equations. And what you may or may not have noticed is that the left sides are actually the same. The variables are different, sure, but the left side coefficients are the same. So in fact, really what you can do is you can solve this system of equations as the following matrix. So I'm just going to write the coefficients 1, 4, negative 1, negative 3, which by the way is just this original matrix, so there's no surprise there, and 1, 0, 0, 1. So basically we're solving the two systems at the same time when this is equal to 1, 0, and when these coefficients with the variables A, C, or B, D, whatever you want to call them, are equal to 0, 1. So we'll get obviously 4 solutions there, or I guess one solution for each variable, so 4 variables total, obviously. And what this really tells us is that in general, we can start with A and the identity, the n by n identity on the right like this. And then what we want to do is we want to basically apply row operations until we get the identity on the left. And what we'll have on the right as a result will end up being the inverse. And I'm not actually showing the details here, but notice that if you were to solve these systems of equations by row operations, that's kind of what happens. You make the right-hand side, or I guess the left-hand side I should say, into the identity. But since the right-hand side is the identity already, we're kind of swapping these. But when we shift this over by means of row operations, the output that we're left with over here ends up being the inverse matrix actually, which is kind of interesting. Now this method works beyond 2 by 2, so this works for 3 by 3s, 4 by 4s, you name it. But it involves row operations and it can be a little bit of an intense process. Okay, so now I'm actually going to show you a generalization of how we can find the inverse of a 2 by 2, by means of a shortcut basically. I'll prove the shortcut, it'll be pretty quick. But kind of remind ourselves, we'll have to remember what the answer was here, and we can see if we can get from here to here quick. In fact, real quick, if you want to take a look, maybe you can recognize some patterns already. And beyond that, let's take a look at that shortcut right now. All right, so instead of proving the shortcut from the ground up, I decided to just recall what we saw in the previous example, try to come up with some guess, and then modify that as needed, because otherwise there's too many symbols going on, it's a little hard to follow. It's doable, but I don't want to make it too theoretical. So notice here, this was our original matrix A, and this was the inverse we got from the previous example. Now, I said to look at the two, relate them, see if you can find some patterns. And hopefully, the pattern you should maybe come about eventually is that, well, 4 and -1 changed signs here, and -3 and 1 swapped positions. So there's this diagonal here, which swapped, and this diagonal here, which were negated. And in fact, that's kind of what's going on. So that's our guess. So our guess from that example, just from experimenting, is that if A is A, B, C, D, like that, this 2 by 2, then A inverse, maybe, is, let's see, swapping these two, so that gives me DA, and then negating these two gives me -B, -C. So what we'll do now is we'll multiply these and see if we get the identity, and then if not, maybe we can modify it. So let's see. So let's multiply them in any order. So I'll just do A times A inverse. So it's A, B, C, D like this. That's B, sorry. Multiplied by our supposed guess inverse, D -B -CA. Now if we swing things around and multiply down and across, here's what we end up getting. So we get AD minus BC. Okay. Here, if you multiply these, you get CD minus CD, which is 0, so that's good. And what do we get over here for the second column now? We get -BA and AB, so those indeed cancel, we get 0, good. And here we get -BC and AD, which actually is the same as AD minus BC. So it kind of looks like the identity, not quite though. What we want the identity to be is 1, 0, 0, 1. That's our identity, not this. It looks close though. In fact, if you think about it, this is really just a scalar multiple of the identity. In fact, really this is just the quantity AD minus BC as a scalar multiplied to the 2 by 2 identity 1, 0, 0, 1. So with that being said, A inverse must really be this, but divided by this quantity here, which is kind of strange. And this actually explains a few things that I kind of alluded to earlier that I'll touch on right now. So this is indeed our shortcut. Now first off, you'll notice that if you take AD minus BC for this matrix here, you indeed get 1. So that's why it looked like only that was happening, because we're not dividing by anything. But in general, you always have to divide by this quantity. So again, this times that's -3, that times that's 4, I guess -4, and let's see, -3 minus -4 is -3 plus 4, so that is 1, like I said. So that's okay. But now remember I said that not every matrix has a multiplicative inverse, and here's why. We can't divide by 0. So if you pick A, B, and C entries for a particular 2 by 2 matrix that you just want to find the inverse of, you can choose A, B, C, and D so that this quantity AD minus BC is 0, and then we'd be dividing by 0, so the inverse wouldn't exist. So there you go. You actually have a way of generating your own examples of matrices that have no, well, 2 by 2 matrices anyways, that have no multiplicative inverse. So that's kind of funny. So now we'll do maybe an example or two involving this. In fact, you know what? Let's do one example using the shortcut, and then we'll do an example of finding a 3 by 3 using the procedure I showed just now before this example. All right, so here we have two matrices that we want to find the inverse of, A and B. A is a 2 by 2, so we'll just use that shortcut. And in fact, this is really quick. Now that we understand how the shortcut works, hopefully, it's going to be 1 divided by, well, let's see. it's going to be that quantity, this times this minus that times that, AD minus BC. By the way, we'll actually talk about this quantity in more detail in chapter 10.4. This quantity is known as the determinant of a matrix. So we'll see that in more detail in the next chapter, or in the next section of this chapter. So it's negative 18. Actually, let me write it down here so we can write it simplified over here. So negative 18 minus negative 10, that's negative 18 plus 10, that's just negative 8. Good. And the matrix that this is scaled into is swapping these two, so we get negative 6, 3 like this, and then negating the other diagonal, so changing their signs, positive 5, negative 2, like that. Perfect. And if you want to scale in negative 8, well, 1 over negative 8 in, you can certainly do that. So let me do that over here. I want to make sure we have some space here. Let me just do this. So I think we can view it. So negative 6 divided by negative 8 reduces to, I guess, 3 over 4. It's positive. Negative 2 over negative 8 is 1 over 4, positive. And that's negative 5/8 and negative 3/8. So this is one way you can actually write the inverse of A. You can leave it like this too, but dividing by negative 8 and actually scaling it in, I think, is not a bad idea in practice. So there you go. That's the answer for part 1. Now for part 2, this is not a 2 by 2, so unfortunately we can't use a quick shortcut. Instead, we actually have to use that process I was talking about, where we're required to basically have this kind of setup, where we write our original matrix on the left, and we write the identity separated by some dotted lines. I think I use a solid line, but you can use dotted lines, doesn't really matter. And then the identity, in this case a 3 by 3 identity, if you recall, is 1, 0, 0, 0, 1, 0, 0, 0, 1 on the right. And now we'll use row operations to transform this side into the 3 by 3 identity. And the result we get here will actually be the inverse. So the only thing is, when we're applying the row operations here, we have to make sure we apply it to the whole row. Okay. Now, if you remember, to get this looking like this, we want to go column by column. So first, I want to zero these out. So I'm going to do that using the top row. So I'm not going to write the actual operations. Like, I won't write the instructions because it'll take too much space. But you can kind of fill in the detail for yourself. But really, to make this 0, I'm going to just multiply it by negative 1 and add it to this. So I'm just doing top minus bottom, basically. So the top row stays the same. Nothing new there. Make sure it's spaced out okay. And the middle one is, again, top minus bottom. So it's 0, negative 1 minus 0 is negative 1. 0 minus negative 1 is positive 1. That minus that's 1. 0 minus 1 is negative 1. And 0 minus 0 is 0. Good. And now here I need to multiply this by 6, the top one by 6. And, well, I guess negative 6, we can do that. And then add it to the bottom one here. So let me write that out, actually. So I got negative 6, 6, 0, 6, negative 6. 0, 0. So this is the top row, it's row 1 multiplied by negative 6. And now adding this to the bottom third row, our result here is, let me write it over here, we get 0, 4, negative 3, negative 6, 0, 1. Good. Okay. And again, it's a little, well, it's kind of tedious, but it's not too bad. Just knowing row operations, basically. We have that separator here. And now we're on to the second column, and I want these to be 0 now. So the top one isn't too bad. Again, it's kind of like a top minus bottom situation. In fact, we could do that, top minus bottom, and then that'll be the new row 1. So now so that was our equivalent matrix, and now we'll get a new one over here. And then after one more, we'll be done, and we'll actually find out what our inverse is. So let's see, top minus bottom. So 1 minus 0 is 1. The bottom middle row stays the same. So row 2 will stay the same in this case because it's not zeroed out. So it's 1, 0, negative 1, 1, 1, negative 1, 0. Good. And again, we're doing top minus bottom to replace the first row. So 1 minus 0 is 1. Negative 1 minus negative 1 is 0. 0 minus 1 is negative 1. 1 minus 1 is 0. 0 minus negative 1 is positive 1. 0 minus 0 is 0. So that's the new row 1. Great. And now I need to multiply this middle row by 4 to cancel this 4 out. So let me show that over here. So multiplying that by 4 gives us this. And then adding that to the bottom row, unchanged, will give us, let's write the result over here. We have 0, 0 now, 1, negative 2, negative 4, and 1. Perfect. Whew, nice. So we're so close. We're almost there. We can taste it. So now all we need to do is 0 these two. And that'll hopefully get us where we want to be. Maybe we can multiply the middle one by negative 1 to make that positive 1, but we'll see in due time. This is already a 1, which is good. In fact, if we just add this to the top one, that's our new row 1. So that's pretty simple to see, I think. So notice the bottom one stays the same, so that's going to stay the same. 0, 0, 1, bar, negative 2, negative 4, 1. And again, adding this to row 1 gives you the new row 1. That's going to be 1, 0, 0, as we expect. And then adding these 3 to these 3 will give you negative 2, negative 3, and 1. And 1. Good. And now, like I said, we probably want to multiply this row by negative 1 to make that positive 1. And that'll be negative 1 now, so adding that to the third row will be good. So let me do that. Let me multiply this by negative 1. So we'll get 0, 1, negative 1, negative 1, positive 1, 0. And then adding that to the original row 3, or this row 3 anyways, what do we get? We get 0, 1, 0, negative 3, negative 3, 1. Whew, nice. So notice, we've gone through this process. We started with matrix on the left, identity on the right, and now we have the identity on the left and this new matrix on the right. So this new matrix better be B inverse. And, well, it should be. I'll allow you to check that on your own. But, you know, I guess just for formality purposes, let me write it out specifically. So B inverse is the 3 by 3 matrix whose entries are negative 2, negative 3, negative 2, negative 3, negative 3, negative 4, and then 1, 1, 1. And I don't think that's too difficult to check. So you can check that when you multiply these in any order, you indeed get this 3 by 3 identity. And you can kind of see how this process isn't the best as far as, you know, it takes a lot of time. But it's good practice on row operations. I know I went through this really fast and I wasn't super detailed on what I was doing. I said the steps out loud, but I didn't write the actual instructions of the operations, which I feel kind of bad about. But again, you can go through it on your own and try to work out the details there. Let me just mention, by the way, there is actually a shortcut for 3 by 3s. It's not the same as this shortcut, and it's not worth for me to go into details of because it involves a lot of weird little steps that aren't very, how do I say, they're kind of beyond the class in some sense. So you'll see those actually in a future class if you ever take linear algebra. There's a kind of nice consequence that'll make you, well, it'll help you find the inverse of any matrix by a kind of different way, and that way kind of explained a little differently with some corners cut is really the shortcut for the 3 by 3. So if you want to look into it, there's, I'm sure, all sorts of different videos and explanations online of how to do that. But for right now, this is the way we know how to do it. And it's not too bad, it just involves row operations. Okay, so I've talked enough about that. Now I want to show one last thing, and it is basically going to be how we can apply inverses to actually solve systems of equations. And it is by far the best application of inverses. So let's take a look at that right now. All right, so now to end chapter 10.3, I'm going to show you these two examples here. They're systems of equations, and I know it seems like you don't have enough space to solve these, but haha, we have a little trick up our sleeves now. So normally you'd expect me to write an augmented matrix, but instead I'm going to write something a little different, and I'm going to label it as ME, which will stand for matrix equation. Now, we could have spoken a little bit more about matrix equations when we spoke about operations and matrices in 10.2, but really there's no immediate use. So I'd rather introduce it here. So here's the matrix equation we're going to look at. So it's going to be 3, negative 2, 5, 3. You kind of see where this matrix comes from. It's just the left side. multiplied by the 2 by 1 xy equals the 2 by 1 8, 7. And I'll allow you to figure out the details of this on your own, but you can kind of see right away what's happening. If you swing this over, multiply down, add across, you indeed get this as a 2 by 1 is equal to this 2 by 1. So that means the top entry must be equal to that one, the bottom one must be equal to that one. So you indeed get that there's an equivalence between this system of equations and this so-called matrix equation. Okay, good. But now, what I want to do really is I want to label these things in terms of matrices and solve the matrix equation. So I'm going to call this matrix A, this matrix our variable matrix X, and this 2 by 1 matrix B. And what I'm going to do now is I'm going to basically solve the equation AX equals B, kind of as you would kind of just with regular algebra. So notice you would want to divide by A to get, X by itself, right? And so X would be B over A. With matrices, we can't really divide, but we can multiply by inverses. But remember, matrix multiplication is very particular on what side you multiply things on by. So I'm going to multiply both sides by A inverse on the left. We get this. Notice since matrix multiplication is associative, we can change these parentheses like that. This is just the identity, and the identity times any matrix is just itself X. So we just get this. Perfect. And we know how to find the inverse of a 2 by 2, so we can do that really quickly. So this 2 by 2 we want to find the inverse of, and then multiply it to B. So that's really all we need to do to find out what X is. So let me try to do that here. So I'm going to find the multiplicative inverse, but remember that we have to divide by the determinant. So let me just make some space here for 1 over something, and then we're going to multiply that result by B, which is 8, 7. I'm going to try to do this in the limited space I have, but I think it's doable. So matrix A, its determinant is, let's see, it's going to be 3 times 3 is 9 minus negative 10. So 9 minus negative 10 is 19. Let me just make sure I did things correctly here. So I got 9 minus negative 10, that's 19. Okay, well, that's fine. And here we swap this diagonal, which doesn't really do anything because they're both the same as it turns out. And we negate these two, making this positive 2 and this negative 5. Great, so far, doesn't really look that great, but let's see what happens. Maybe it ends up being nice, who knows. So let's swing 8, 7 over, multiply down and add across. And we still have that 1 over 19 on the outside. And this, by the way, is going to give us X, so it's fine. So we have 1 over 19 on the outside, and then hopefully we can resolve this pretty quickly. So multiply down and add across, we get 24 plus 14. What is 24 plus 14? That's 38. Good. And then below we get negative 40 plus 21. Negative 40 plus 21 is negative 19. And these are both divisible by 19, so if you scale the 1 over 19 in, we actually get 2, negative 1. Wow. So that means our solution is actually the ordered pair 2, negative 1. Because, of course, the top entry corresponds to X, the bottom one corresponds to Y. Wow. So I know I didn't do it in quite the most space available, but, you know, with the space we had, I think it was fine. Now, I want to try to solve this one in a very similar manner. But, of course, we saw that to find the inverse of a 3 by 3 took a little bit of time because we don't have a shortcut on our hands that's usable as of right now. But just bear with me, believe me, it's doable for us in our particular case. And you'll see why. So I'm going to write this, let me border off our previous example here. Now let's write this as a matrix equation. That's M. And our matrix equation is, so converting the left side into a matrix is 1, negative 1, 0, 1, 0, negative 1, 6, negative 2, negative 3, multiplied by the 3 by 1 matrix X, Y, Z is equal to the 3 by 1 matrix A3, negative 2. A little bit of space. Yeah, there we go. And good. So now we know how this goes. We're going to label these accordingly. This is our matrix A, this is our matrix X, and this is our matrix B. And we know that to solve the equation AX equals B, the solution is just X is equal to A inverse B. the algebra is the same as it was here, over here. Sure, the dimensions of the matrices are different, but the algebra still behaves the same as it turns out. Great. So now, again, how do we find A inverse? Well, luckily for us, we already did this one. In the previous example we saw, I gave you this exact matrix. And we actually found the inverse of that. And, well, let me write it out for you. So I have it right here. We got -2, -3, 1. -3, -3, 1. And -2, -4, 1. Great. And we're going to multiply this to b. b is a3, -2. So now we're going to swing this over, multiply down, add across. So notice that the majority, the majority of math that happens really in this process is finding the inverse. Once you have finding the inverse down, then solving the system is actually pretty simple. And that's kind of the magic that happens, and basically the beauty of this application of multiplicative inverses of matrices that I really wanted to show to end 10.3. So now if we multiply down and across, the numbers may get kind of large, but let's see. So remember that this matrix X is the entries, 3 by 3 matrix with the entries X, Y, Z. And we get -16 minus 9, so that's -25 minus 2, that's -27. Okay, so it's a -27. For Y, we'll get -24 minus 9. -24 minus 9 is -33, minus 2 is -35. Great. And then here we're going to get -16 minus 12. -16 minus 12 is -8 minus 2. Let me say that again. -16 minus 12 is -28. Minus 2 is -30. All right, so that means that our supposed solution is -27, -35, -30 in that same exact order. And I'll allow you to verify this on your own. I don't think it's too hard to verify, especially for these first two, because they only involve two variables at a time. But I'm pretty certain this is correct. This one we could have checked pretty easily. This is going to be, let's see, 6 minus, well, I guess double negative, so plus 2, that's 8. Here this is 10 minus 3, that's 7, good. Maybe we can just try it. So we get -27 here, positive 35. The difference there is 8, good. Here we have -27 minus -30, the difference there is 3, sure, good. And then 6 times -27 minus -35 times 2, so it's going to be positive 70. And then that's going to be double negative 90. So we have 70 plus 90 is 150. 70 plus 90 is 160. And then this better be -162 to make that be the case. And I think it is, because 20 times 6 is 120. And 6 times 7 is 42. And notice 120 plus 42 is indeed 162. So again, you can verify the details on your own, but this certainly works. Awesome. So again, that's it for 10.3. I'll see you in the next video for 10.4. We'll be talking about determinants that I just kind of briefly mentioned in this section in greater detail. And I'll see you then. Thanks for watching.